This panel is on streamlining operations and analysis. So as we said this morning, there's a whole other community of operators who don't really live in that digital engineering life cycle, but are the recipients of the products that we produce as a result of that process. So we want to visit today how we can support that. And we started talking about that a little bit in the panel earlier. Before we kick into that, I'd like to introduce a couple of concepts. They kind of came up initially in our conversations this morning. There's a whole bunch of terminology that we're using. So I just wanted to level set on a couple of things because even for me, this has been quite a bit of a learning curve. So I want to talk about a couple of things like a digital twin, the concept of the Internet of Things, and we've been talking about digital mission engineering because these will be important concepts, and specifically in the context of how they could be used in operations. And to sort of set the stage here, I took a look at what's actually going on in commercial industry right now. What of these things are actually being used in an operational context? So I'm going to show you here an example, and this is an industrial pump being used in a processing factory, or at least a simulation of that. But these technologies are available now and are being used. And the view you see right now is the physical pump, the physical twin. Some of the labels you see on that are actually virtual. So what you're seeing here is an augmented reality view seen through the eyes of a technician using augmented reality glasses. And because there is a digital twin in the background, and because there is sensor information coming from that physical pump through an Internet of Things interface, those things can be married together so that the technician servicing this pump can see what parts are functioning, what the critical values are for that. So in the operational context, that sensor information, telemetry if you will, is being fed back through an Internet of Things interface. So an operator could get a view like this. And this is kind of a simple-minded operational concept for somebody responsible for operating a pump. And that technician just shut off a valve, and you could see immediately that an indication was given that the pump is malfunctioning. And you can see the data displays that are coming about because of that. But here's some of the real magic. Behind that is a full physics-based virtual twin that somebody can look at and understand, okay, I understand that the flow into this particular part of the pump is not correct. What's actually happening? And you can see the physical effects of the cavitation inside of the pump not working. And this gives full information to operators on how to address this. So these are how some of these concepts, like a digital twin, which is a virtual replica of a physical system being driven by Internet of Things feedback and sensor information, can assist someone in an operational context. And what we're talking about here transcends the operation of a particular device, in this case an industrial pump. What we're talking about here is how do we apply these to the mission context. So in this case, what is the mission context? So if we were going to extend this analogy, we would think about the plant operation and the output of the plant as the mission in which this pump is incorporated. So there'll be many pumps, a lot of other industrial equipment, and there is somebody or some people who are responsible for maximizing the performance of that operation, ensuring uptime, guaranteeing quality of output, guaranteeing the quantity of output. And if this pump failed in such a way that it was not serviceable, for example, maybe it's buried and it's going to take a week to get to it, those individuals, through digital mission engineering and the combination of digital twin IoT data, would be presented with a range of options to say, how do I maximize my operational effectiveness, given that this pump is failing, I know what's wrong, but I can't service it right now. What should I do? So that's really what we're talking about here today. And we're talking about that in the broadest operational context. So the before, during, and after. The mission planning, the real-time operations, and the after-action analysis. And I'm very pleased that we have a really great panel that's going to help us go through this. So introducing our panelists, from the far end, we have Curtis Bell, who is from Kratos RT Logic. Curtis is a product development engineer and a product manager for their channel simulation product. So if you haven't seen that in operation, the channel simulator does a great job bridging the virtual world into the physical world. and we worked with RT Logic for quite a while making that happen. Next up is from Ansys is Sergio Melais. He is a sensor application engineer, a senior application engineer at Ansys. You met Paul this morning, and you met Jim earlier as well, who is a retired Rear Admiral, not General. I guess I didn't really need to repeat that, right? And over here on my right is Zach Cuseo, who is a senior engineer with ASI. And right here, right next to me, is Mike Wasson, who is AGI's Senior Director for DoD Space Operations Business Development. Prior to coming to AGI, Mike retired from the Air Force as a colonel, where he was a division chief for Space and Missile Defense at STRATCOM, and also division chief and deputy director for the Joint Space Operations Center. So Mike has a unique perspective, both from the product side and the mission operations side. So leveraging off what I just talked about and what we talked about this morning, given all the capabilities that are coming out of these engineering processes, the question before us now is, how can we take advantage of these to streamline and accelerate operations and make operational decision-making better? And there's a whole universe of stuff that we're doing, right? We just talked about a few really simple ones, but it's a massive and complicated process. So if we were going to advise the community, either the operational community or the product development community or the integrators, where should we start? What do we think can be the outcomes of this process or the outputs of this process that could deliver the most bang for the buck? And Mike, since you're closest to me and you have a foot in both camps, why don't we start with you?
Thanks, Kevin. So I think in today's operational environment, you're seeing a huge revolution across Air Force Space Command and related units for innovation. There's something called unit innovation funds now, and you're seeing an influx of new young talent in all of these organizations that are being challenged to develop new concepts of operation, test the status quo, and to find different ways to use some of these legacy space systems. So I know that it's very difficult, very expensive to test new tactics and new concepts in space. What we used to do in the past, and are still doing to some extent, is as a satellite gets old, you'll move it out of operations and then into a space test range for the purpose of doing tactics development. And that's opportunistic, but it is not comprehensive. And so having and leveraging digital mission systems and digital twins can allow all this innovation to occur at a level that is much beyond what we have traditionally done over the last 20 or 30 years. So it allows these tactics to be tested in an operational environment, in a physics environment, in a way that you can leverage these systems for low cost and ideas to vet out these ideas before you have to test them operationally on these multi-million, hundreds of millions of dollar satellites.
Thanks, Mike. Jim, you started talking about this in the earlier panel. Want to extend some of the thoughts that Mike shared?
Yeah. So I think when you start to think about these digital models and what you're actually building, what you're really building, in effect, are decision aids for the warfighter. You can envision a future not too far distant where the models that you build of the physical and virtual systems that comprise the warfighting capability for the soldiers, sailors, airmen, and Marines are actually in the field being utilized to help that warfighter make a decision. Just to show hands, how many folks in here read Pete Singer and August Cole's book, Ghost Fleet? A couple? I highly, it's about 5 years old now. If you haven't read the book, I'd highly encourage you to pick that book up. It's the mythical account of World War III and how it might occur. The interesting part about the book is that the hero of the fight is USS Zumwalt, DDG-1000, which, for those of you Angelinos who can get down to San Diego, you can come down to see her. She's sitting by the pier at 32nd Street. It's a stealth guided missile destroyer. But the interesting part about that is at one point in the book, and I won't give it away, they basically turn the ship on automatic. meaning the models are what are deciding how to fight. For those of you who get a chance, there is a very great video that's out right now that was built by Naval Information Warfare Center Pacific. It's at the TSSCI level, but if you got the tickets, go see it. That also talks about a capability they call Kennedy, and Kennedy is the Navy's version of Alexa. And during that video, the skipper basically says, "Kennedy, what should I do?" And Kennedy goes off and runs your models to help the skipper figure out, hey, for this specific scenario, option 1, 70% probability of effectiveness. Option 2, 55% probability of effectiveness. Option 3, forget about it, don't execute that, right? But we're in an era where the differentiation between us and our adversaries is the speed of decision making. Understanding how your systems and fit into the grander system of systems and how they can impact the mission and delivery of capability is what's going to be important. So we're not building these models for just development. We're actually building them to eventually become real war-fighting tools, and I think that is the one significant difference that you ought to walk away with.
Right. Paul, I know in your focus you have responsibility to make sure these processes work both for the creation of systems, the building of systems and the associated software, but also all the way through the entire life cycle. How do you see that kind of vision evolving in your practice?
Yeah, I think there definitely is a lot of pressure on the sustainment side to lower our cost of sustainment. I think it's really lots of easy examples on the space front, because we have all kinds of missions where one chance to get it right, or in some cases the mission is taking shape in space. So you have to have real-time operational feedback loops to what's happening for in-space construction missions. We launched 2 weeks ago our first mission extension vehicles. So a satellite to go up and dock with your dying satellite to refuel it, boost its orbit, extend its life. And there's all kinds of complexity in that mission, right? You're going up to a retiring satellite that now has lost all propulsive control because it's out of fuel and it's just tumbling, and you got to match that tumble and dock with it and refuel it and provide power services to it, and that whole mission life extension from an operational standpoint, it's quite complex, right? And to be able to manage that real time and be able to make decisions down here, a lot of missions we don't know that's going to be the mission, right? So I think it's having the continuity back to the original mission planning, but then how do I make adjustments? How do I think the Dawn spacecraft's a great example. We built the Dawn spacecraft that went spacecraft to kind of in-depth explore multiple celestial bodies, but that wasn't originally the plan, right? It was going to go just to Pluto, and then we decided to go over to Ceres and extend that mission. And so how do you track that operationally, right? I think there's a lot of examples there, but those examples extend, to the sustainment side of a lot of our military platforms, right? How do I simulate the life and mean time between failure and uptime, and a lot of transitions happening. You see it in the aircraft world where I don't sell you a jet engine, I sell you power by the hour. So it's the same thing. I sell you flight hours instead of maybe an aircraft, right? So what's your cost per flight hour, and how do we lower that? And I think having rich models that help us understand those sustainment phases of the life cycle, so that we can understand where are the bottlenecks, where are the pain points, where are the high cost points, and drive those down, I think is really pretty critical.
Yeah, that's a great point. In our last version of this last week, we had Tammy Katz from Sierra Nevada talking about launch services, and in that case, she owned the entire life cycle. She provided a service, but everything from concept development for the vehicle to sustainment was their responsibility. So they had a unique focus on that, and I think that's probably an important point all the way around. But sticking with the space theme for a minute, Zach, maybe I could ask you to comment, because for some of the work on the GNC side, particularly autonomous vehicles, you kind of see this going all the way through the life cycle right now. So what's your perspective on the impact of these digital models through the life cycle, but definitely into operations?
Yeah, so I think the idea and the concept of a digital twin and having a model that you can take from the beginning of a mission all the way through the operations of the mission is super critical. A lot of the times we see, in the design phase, GNC engineers, different subsystems engineers are so singularly focused on creating tools and doing analysis to prove that they can meet all the individual requirements that the spacecraft has to meet. That's their sole focus, and they're writing those tools with that focus. That doesn't really transition well into operations. An operations engineer can't really take that tool then and run all the different cases they need to run, and they end up either using a different tool or have to dramatically rewrite that tool once they get into operation. So if you start with the mindset of, I'm going to create a model and create a tool that can be used by the operations team, that's very critical to adapt and be able to meet your mission requirements.
Yeah, great point. I'd like to revisit that in a minute, but before we do, maybe we could pass the mic down to Sergio. One of the things that I've heard with regard to this is we need to think a little bit about levels of fidelity and where those levels of fidelity belong in operational decision making. Ansys is very much at the detailed physics level. We saw an example of that with the industrial pump. What's your perspective as provider of digital twins with the full physics level of fidelity? Where are you seeing an impact, and how would you advise the operational community?
Well, being able to not only take advantage of one physics, but all the different physics that would need to be taken into account when you're building something. Also having a good communication with operators in the field. Typically you have designers that are coming up with a product and they have some specifications that they have to meet, but the end users are the operators in the field. So also having a good communication of what are some of the aspects that they're seeing when they're out there, from a multi-physics standpoint. Yeah, that's also very important. We can take advantage of our software tool to try to accommodate for that and get a very accurate result as fast as possible as well.
Great. Yeah, good thoughts. Curtis, how about you? I mean, you help bridge the virtual world to the physical world, and we've worked with you in that regard. Any thoughts about how you see these models transitioning into operations and where you've seen that effective?
Sure. So operations, obviously, like we've talked about, right? They're not always the engineers that are looking at the physics or generating the models themselves. And in the end, what we're generating with these models, what we're using them for is the operation, is for the person to sit in the boat and do what they need to do, or launch the bird and have it work the way it's supposed to work. And so what I've seen is the potential from this kind of discussion is to see training early on and have that feedback loop from the end operators. When you have these high fidelity models and you're able to bring it into the hardware or bring it into a user interface that the end operator can now work on, you can start to generate these models, these systems early, put something in front of the operators and say, now go use it. Tell me what you want to see, what you want to work with, and find where those errors are, right? Maybe the model doesn't work quite the way it needs to, or the user interface isn't what we're looking for. The human element of the operator is really what we're shooting for, right? And no matter how much work you put into the model, it's the human on the other side that has to read it, that doesn't necessarily have the technical background. And so when you're working with specifically hardware in the loop, you're able to train people on that and bring those digital models back, right? Rework those systems early on in the process and not at the end result or the final delivery capability.
Great, thanks. So how about you guys? I'm sure we have some practitioners here. We have a question in the back. Any thoughts from an operations perspective about what you think would be useful, or insights from the other side?
Absolutely. So I work with the NAIL, which is the Naval Amphibious Liaison Element, to the 613th Air Operations Center at Joint Base Pearl Hickam. And I work in the strategy division. And basically, we take whatever guidance comes from the flag, and we're supposed to translate that down into orders and plans and things like that. So the Air Commodore will say, we'll give him his brief. Here's the enemy we've got, Peel, sir. And the first thing he'll say is, well, I want to blind him. And then he'll walk out, and that's your direction. That's all you've got, right? And then you'll go 4 days later. You look at the air tasking order, and you see not a single radar on the list of targets that got struck. So those kinds of silly problems I run to all the time, where I'll strike the same target 3 times, 3 days in a row. Oh, you missed the first day. You missed the second day. And then operational assessment finally gets back and says, oh, you really did kill it on the first day. Too bad you wasted about $40 million worth of weapons. So those are kinds of problems that I wrestle with as I'm coaching people through different things. What I'd like to hear about from the team is those kinds of things, but also, so in 3 months, I've got to go to an exercise where they're going to say, hey, we're going to give you 2022 weapons to peel this onion with. And I'd like to hear more about how the digital twins are going to be integrated into that kind of environment where I can run different scenarios of, say, this deep strike system over here, this deep strike system over here, and do cost comparisons and effectiveness and things like that. Okay, how many souls did I lose and how many dollars did I expend to achieve that objective? All those kinds of things I'd like to hear about from the panel as we continue to go on.
All right, so we have at least a couple questions in there. One is, how do I understand the outcomes of the mission after I executed it so that I can be smart about how I do the continuation of the mission? And then, how do I deal with future capabilities? How do I get that into the process, and how do I train my operator? So why don't we break it into those two parts? So anyone want to take the first part of that with regard to the mission outcome assessment?
Yeah, I'll speak from the Air Force side. I really would like that too. This is a culture shift. So I can say from an ops perspective, you can see in the acquisition world where you're going to now transition into these exquisite digital models that are operating in a physical environment. Great, that's going to inform your acquisition. What I don't see is how that bridges into the ops world. How do we incorporate that into our training systems? How do we incorporate that into our common operational displays? There's been little emphasis, little focus on that. And so if it's not part of the culture of the day-to-day operator that's using these systems, then how are they going to interface with those kinds of systems in a test and training environment? You go to these war games and you go to these exercises where you're working future systems, and today you're doing that with white cards and PowerPoint. And those concepts are very difficult, especially when you're talking space systems, is where my focus is. It's just not intuitive how objects move in that physical domain. So I think part of it has to be, the first step has to be to bridge that gap and incorporate it into your day-to-day ops.
Yeah, I'm going to follow up because I see the same problem from the Navy perspective, right? The campaign level models are devoid of reality from the perspective of the underlying systems that support those campaigns, right? So there's an immediate disconnect between what the campaign level model tells you is really happening and what the underlying capability of the system that supports it is. A great example of one that bridges the gap, like I said, is that Aegis digital twin, right? So if you said, hey, let's just say had a ballistic missile scenario, right? And you wanted to say, did you shoot down the adversary's ballistic missile? The reality is you can run the Aegis digital twin right now, which is the underlying basis for the real combat capability, and be able to say absolutely with 100% certainty, yes, I fired the missile, and yes, the missile hit its target, right? Today, the campaign level models that the Navy has doesn't do that, right? It just says, okay, yeah, I know I fired the missile, but I really don't know that it actually had the right accuracy to be able to capture the missile. So it provides you with some statistics that say, oh, here's BDA. There was a 35% probability that the target was destroyed. Well, that doesn't help the 4-star make decisions, right? The 4-star wants to know, did it happen or did it not, right? It reminds me of the old George Carlin joke where he said, I'm driving behind a truck and it says, inflammable or unflammable. And he said, look, when you're going 90 miles an hour and your brakes are done, I just want to know one thing. Is it going to flam or is it not, right? So we got to get to that point where the underlying models are there. But that's a huge transformative capability, right? That means that every program of record weapon system is delivering some digital capability which then can be federated into a campaign level model that bridges the gap between the virtual world and the reality of warfighting.
Yeah, we used to run these models, this was probably 25 years ago, and trying to ascertain the impact of a new space system. And the models we were using back then, we had a dial that said a little bit more space or a little bit less space, and the way we measured it was how far the forward line of troops moved in a day. So, that's the kind of fidelity that we're used to.
I've got a leader that likes to talk about digital twin density, right? So we have digital twins today, right? We have these models that we can use many of them in an operational sense today, but we need to increase the density of that to be able to deal with any scenario. And there's areas, like this gentleman pointed out, where we've got some osteoporosis, right? There's not enough density in that bone, and I think that, and it gets particularly challenging in this system of systems modeling perspectives, where I'm taking mission models from multiple domains and trying to combine them together. One of my chief engineers, our chief engineers for the company is here, and we were having this discussion this morning as how do we deal with that complexity of cross-domain mission modeling, and it is challenging, right? There's still work yet to be done in that space to enable that, and I think it also gets complicated. One I think is awareness, right? It makes me sad when, whether it's a manufacturing operation person or an operations person out in the field, it makes me sad when they see a mission model, and I ask them, like, how long have you been working on this given system? And they're like, oh, I've been working on it 3 years. I'm like, oh, well, let me show you this. And I show them a mission model, and they're like, I had no idea that's what I was working on, right? And you're like, oh, we got to do better. We have these models, right? How could we do better? From a training standpoint, we could do better there, but then I think the IP side of things, I think, adds a layer of complexity, right? We get ourselves just spun in knots about who owns what, and at the end of the day, we've got to, I think, get past some of that so we can bring these multi-domain models together and enable these type of real-time operational decisions.
Yeah, great. And I think you referred earlier this morning about mission engineers sort of having 3 heads operating at the same time, having like a 360-degree view, and I think that's important. But our question also broached the topic of new and emerging capabilities, and several of you have already brought up the notion of these capabilities have to be accessible and usable by the operators. So why don't we shift gears for a moment and talk a little bit about the operational training and readiness for the operators. How can we bring or get operators ready for new capabilities? How do we vet out new techniques, tactics, and procedures? And how do we take advantage of some of the technologies we're talking about here to begin that? Does anyone want to begin that process?
I can jump in just quick. So I get to work with all these former astronauts. It's so cool. Like, you're walking down the hall, you're like, oh, hey, former chief astronaut, Charlie Precourt, how's it going? And they really challenged us in some of our business units to say, you know, when you're training for a mission at the International Space Station, everything's done in virtual reality, right? 100%, because you have no other way to train. And we have all these scenarios where, from an operational standpoint, whether I'm going out to maintain a system or maybe I'm assembling something, or I'm doing a safety-sensitive mixing operation of a chemical propellant or something, how do I train that in a virtual scenario? And I really do believe that we're getting really close, right? The form factor's not quite there yet, right? I've got my HoloLens 2 already, even though there's some issues with them. They're getting way better, right? And they're getting smaller. And when they get down to the size of just, you know, your regular pair of glasses, you're going to see a fundamental just transition in that ability to train and leverage this technology. But that's only going to be, I keep dropping on my business cards, that's only going to be helpful if we have the fidelity of our digital twin mission models ready to feed that pipeline, right? Today, I've got to build Unity gaming engine scenarios for some of that operational training, and it's way too expensive, right? And so being able to use tools like STK to throw together a quick mission scenario from an operational standpoint that I can do in 5 or 10 minutes and then feed that into a training scenario that I can pump operators through is going to be really, really powerful.
Sergio, maybe if you can extend that. I mean, I watched the video with the industrial pump. I was really entranced by the colors on the pump, and that's kind of the extent that I understood that. What are you guys doing to make that kind of information accessible and actionable on the operational phase, and being able to extend that to new technologies that are coming on board?
Well, in simple words, it's better to fail in the virtual world than in the real world, right? So we can model different scenarios, different different components in different ways, so we can actually, from our tests, from our virtual tests, we can come up with some suggestions as to what are some good procedures, good practices to people to follow. Obviously, we're doing it in the virtual world, so no harm, no foul. So yeah, that would be a good recommendation.
Good. All right, any other comment?
Yeah, so I'll take that. One of the things that we've done, and again, going back to if you have a really good digital twin, you can start that training so much earlier in your life cycle. I was on a program where we came on and we did the software for a satellite, and the company that was building the satellite was not going to be the operators, and NASA was actually going to be the operators. And NASA kept saying, hey, we need to start getting our ground data system going. We need to start training our operators. And the company building the satellite said, oh, well, we don't have, we can't send you any hardware yet. We don't have that built up. It's not ready to go. Well, what we did is with our digital twin running in STK, we actually used Solus and STK, hooked it up to their ground data system, and actually before AIT even started, NASA was actually training their operators and getting their ground data system developed and tested.
Great. All right, audience, how about you guys? So hopefully that addressed the question that was posed. Anybody else have thoughts with regards to what technologies are going to be impactful? How do we support the operational training of our operators? Or any experiences that you'd like to share that offer insights? In the back.
Be careful, Kevin. No, I mean, this resonates with me a lot. We worked on a program with US Stratcom, I don't know, 6 or 7 years ago. And the commander of US Stratcom was Admiral Haney at the time. And they had this war game where, as Mike was saying, there's a white card. Admiral, the satellite was just destroyed. And he's like, okay, what is the impact to my mission? And they turned around and the official answer was, oh. And you can't go to your 4-star with that kind of answer. And so they brought us down and we got to see the operations center where they do this. And there's literally dozens of different systems. And there were literally 18 different maps. And each map showed something different of a different system. And the Admiral was saying, look, I'm a smart guy, but I cannot synthesize 18 different maps in my head and pull all this information together to make a decision on the impact of space and air and all these strategic systems together in my head. And so the ability to pull all of these different models together across different domains, I mean, it's just so stark. It was just such a stark reminder that this problem has been a persistent problem, but I think that the technologies that you guys are talking about is enabling these types of systems to be brought together so that you can fuse different domains, fuse the model of how that system, so that when you're in a war game or in a real operation, you can say to what Admiral Rodman said, what is the cost or the benefit of option A versus option B? I mean, that's exactly what people are looking for, and to take the model of these systems, how they perform, and how that's going to impact a decision, so that you can come to the decision maker and say, here's option A, here's option B, there's risk with this, there's risk here, but now you, sir, have to make the decision of what to do with that information. I think that's critical.
I mean, it's funny, Adam, right? So we have that today in the commercial sector. I mean, how many people here use Trivago or any of the other sites, right? I mean, it's pulling data from multiple sources, right, to tell you, hey, this is the cheapest hotel room in Manhattan Beach. If you happen to be going there, here's the hotel room, here's the cost, here's the number of stars it gets, and then, you basically got enough information to make a decision about where you want to do, whether you're doing it for airlines or whether you're doing it for, hotel rooms. I mean, the reality, right, is these model-based system engineering tools, the whole purpose behind them was to put the data in a form that's shareable across multiple entities so that it can be rendered effectively based on the user's specific requirements. And I think the thing that frustrates the hell out of me, right, is we're still in a keyboard, mouse click world, right, where everybody else, including our, soldiers, sailors, airmen, Marine, guardsmen, right, are in a video game world. And, I was just at an industry day for a capability called Spectral, which is surface comment for the fleet. Right, on the current Sea Anchorman F system, and this is no offense to the builder who is, Boeing Argon ST, some actions on that system take 159 mouse clicks to do. Now, if you're an operator, right, do you really want to do 159 mouse clicks to do anything? The reality is, with model-based system engineering, right, you can collectively build up modeled capability, right, to be able to make the operator's job a lot easier. And the sooner we bring the operators into the fold up front is where we're going to find a lot of success. And I'd argue, as a longtime NRO guy, right, I think one of the success stories that we can tell from the national security space side was bringing the operators into the systems very early on to say, what capability do you really need when I go to build that spacecraft or when I go to build that ground system, and then model it effectively in tools like STK to show the impact of those changes on the actual developed system. We got to get there, and I think model-based system engineering is the way to get there because of the the commonalization of the data and the ability to share that data robustly.
Yeah, great point, Jim. And maybe if I could leverage off of that. So your specific description was getting the operators involved earlier on so that we're delivering the products that work the way the operators need to. I guess one thing I'd ask is, and leveraging off of Adam's comment, I'm familiar with that war game and others like that, and in some cases, the war game was pretty well laid out, and we built a scripted environment specifically to support that war game, and we're 2 hours into it, and it's playing out completely differently. And in a world where we're not really sure how the mission is going to evolve, what is the composition of the operations team among operators as we think about them now classically, among DevOps teams that are now integrating new scripts, workflows as we're getting smart, among engineers who kind of can look at that pump virtual digital twin and say, okay, I understand what that means. Do we need to change the way that we think about our operations teams because of these technologies coming online?
I've heard somebody say that the sailors of the future will be data scientists, not necessarily just pure operators, right? Perfect example, I'll go back to USS Zumwalt. The ship produces about 1 terabit of data a day, all right? And this ship is the size of a World War II heavy cruiser, which, if you look back at history, World War II heavy cruisers had a crew of about 430 to 550 people. Zumwalt's got a crew of 156. And the idea that, I expect some, poor petty officer to understand exactly what that complex, electromechanical, power generation system, by the way, the power plant aboard Zumwalt produces 78 megawatts of power, right? And it's an electric drive ship. So that operator has to have fundamentally different skills than the operators that we have today. It gets back into this idea of, being able to not only train the sailors appropriately, but also identify what skills they need. The skills that we're going to require our operators to need tomorrow are not the skills that we require our operators to need today. And the Navy frankly is struggling with that. We're struggling with this idea of how to make sure that we select the right people for the career fields that they're going to go in. The idea that we can use those digital twins and those models up front to help us select the right sailors with the right skills, right? I can envision a day where, when we bring sailors into the fleet, the first thing we do is we give them an aptitude test that's based on the digital twins that they're expected to, or the systems that they're expected to actually go operate, to see whether their aptitude is A, B, or C, and appropriately slot them for the right system or the right training that will provide them with the ability to operate the system that they're going to be tasked with. And that's not just operating, it's also understanding what the system is doing and understanding what the warfighting capability of the technology that they're being given. And again, I think it's, like every service, we're going to ask our warfighters to do a lot more with a lot less in the future than we are today, simply because the cost of the technology continues to escalate.
Right.
Yeah, when I came in the Air Force, I was in a satellite operations squadron that had 150 people, 135 of which were engineering graduate officers, and we certainly can't replicate that today. So we spent 12 months in training, going through detailed schematics and every wire diagram you can imagine on all the subsystems on that spacecraft. And there's just no way in today's environment that you can replicate that. So you need to replace that process with the digital twin and the systems-based engineering processes. And that will not only reduce the complexity of that 12 months of training, but it'll also accelerate it.
Thanks, Mike. I'm going to change gears here a little bit, so I appreciate everybody's inputs, and I definitely want some audience participation here because I've had several conversations on this topic already this morning, and I know there are several strong opinions out here, so hold those opinions and please raise them when I ask for questions. But maybe we can start with you, Curtis. So we're talking about models being used for operational decision making. Paul, you several times brought up the point, it's like, look, we get one shot at this, we can't be wrong. How do we make sure that these models are of a level of validation that they are that trustworthy?
Thanks, Kevin. Yeah, I was going to bring up something like that as we were talking through this. The fundamentals of what we're talking about from the war games is trust, right? We have to be able to trust the digital models that we're generating and be able to adapt to an ever-changing world, right? No customer ever changes requirements midstream, right? And so it's our ability to adapt to the ever-changing environment and the trust in our models that we're putting together. In particular, machine learning, and I know we talked about this a little bit in the previous panel, is going to be able to take that data that we're creating, these huge streams of data that the models are creating, and crunch those numbers and put that in front of an operator. But now these models have to be verified, right? We have to be able to put that down somewhere. And trust that the model does what it's supposed to do. And so regression testing or edge testing, edge-to-edge testing for systems, when we're looking at these new hardwares, these new technologies, it will inevitably have to be that we're testing hardware in a lab to generate the models, right? We can do a lot with physics, we can do a lot with algorithms, but when the rubber hits the road, we really have to be able to test the hardware. We have to be able to test the technology. What is it like when we put the amplifiers together, when we put all the wiring diagrams and all the rest of that together? And so it will be, how do we test and build these models cheaply without flying necessarily the multi-hundred-million-dollar birds, and verify that they operate and that the models match that. I guess that's the real, and the way we do that is, and not to plug my own technology here a little bit, but really is hardware in the loop testing, right? We have to be able to put the hardware down and test that and feed that data back to the model. So there's the model that's creating the test scenario, and that's being simulated on the hardware, the new technology, the next technology that's going on, and the data and the response of that technology from whether that be IoT or a system level is being fed back to the model to fix the model, to make it a higher complexity, to make that fidelity a little bit better, right? And so when we do that and we run those regressions in the edge-to-edge testing, we create a lot of data, but there's trust in that data. And so we can't expect a human operator to then take all of that and say, yep, that looks right? I mean, that's going to take a long time for us to do that. To pick that up, we need machine learning. We need distributed processing capabilities to do that. And so machine learning is going to be able to run those edge-to-edge cases and see the patterns, the ability, the data that's coming out of that, and then extrapolate what would the next piece be. And that's how we're going to adapt to the changing customer need. Customer A says, okay, now I'm going to run at these frequencies, or I'm going to run into this war game, or I'm going to run into this situation. You can't necessarily develop a hardware on the spot, but if you've machine learned over what's going on, if you have those regressions, you can go back to the big data and say, okay, crunch the number, now that you understand RF environments or satellites, go change and tweak this one piece. What do you think it's going to look like, right? And a human operator not necessarily can't do that. But if you have the hardware in the loop background, the regression, edge-to-edge testing, and the machine learning on top of it, you start to build that trust profile so that when the machine comes out ahead and says, this is what it's going to look like, you have a set amount of trust and a certain capability to say, yeah, I think that's the way it's going to work, and this is how we're going to adapt to that. I guess it's a really long answer to a short question.
Yeah, very good. All right. Sergio, maybe the same thing. So I know you guys must get asked occasionally, how do I trust your answers? How do I know their validation? Do you see things similar to what Curtis mentioned about incorporation of hardware in the loop, AI to ensure validation?
Yeah, I mean, obviously the easy answer is what you design, you gotta test and measure, and the results should be the same, right? But we've been around for a long time, and we take advantage of our experience, with our codes and developing automation to make things more accurate, more efficient, run faster. We collaborate with a lot of customers to take some of their experience as to how we can make things more efficient and run better, and actually get to the right answer and give them exactly what they want. And we can, like I said before, we can test different scenarios so we can figure out what's the best configuration that they will require for what they're trying to do, so they can get to the answer quickly and right the first time.
Great. Go, Paul.
I think, Kevin, I think the best example to me, when I was in Milford, Michigan at a General Motors proving ground, and we're on this tour, and if you ever get a chance to go do that, by the way, driving a Corvette 100 miles an hour or just thrashing a Suburban over these giant potholes, it was the best, right? But we're driving along, and there's all this rusted junk, looked like to me, overgrown with weeds, and I'm like, what is that junk? And they're like, oh, those are dynamometers. And I'm like, well, why are they all rusted? Why do you need all that junk there? And they're like, well, when we used to offer your 70,000 mile warranty, we'd run your car 100,000 miles out here physically, and we did this test physically, and that's how we validated. But I think the auto guys have had an advantage. So they do that all virtually now, right? That's why these things are rusted over. And their crash building was just as fascinating, right? So they used to crash like a car of every model, every day, all the time. And they got to the point where they were able to validate their models to the point that now they just crash one model for a given platform every month. And the only point of that crash is to validate their virtual simulations. And I think in the aerospace defense world, we don't have those rates. We don't have that luxury to validate our models. So I think it just adds a sense of urgency to me, right? That every test event, it's a gold mine of data, and you've got to be validating your models, or you're missing an opportunity, right? You're missing an opportunity to build that trust that otherwise would get lost. And now not just validating my models, but validating these hardware in the loop scenarios, validating how I'm simulating those models so that I can build trust in the overall scenarios.
The ship is collecting 1 terabit of data a day. What are people doing with it? Absolutely nothing.
Yeah. We have a question in the back?
The one thing I'd like to add to what Sergio was talking about, if you think of digital twins have a maturation process as well. Your first digital twin for a certain system might be 1.0. Over the years, you might get to 12.0, 13.0. Every time you get a physical test, yes, you get to tune your digital twin, but we're even seeing times when we're asked to use 2 different solvers or take 2 different methods for simulation and tune simulation against simulation, and then take that against measured. So what we see is, in let's say the new environment, a model-based procurement, whatever these first models are that are coming out, they're gonna need a tune-up every year, they're gonna need an oil change, you're gonna have to keep them relevant. All the new information that came off that ship that wasn't used, what's most important metadata that can tune that? Then guess what? Within 15 years, maybe a whole lot sooner, those models are gonna be money. They're gonna be right on there. But we see a whole generation of kids coming out of college, and they're gonna be digital twin pilots. They're gonna look at legacy data, and their job is to care and feed for these digital twins, and they're gonna be the lifeblood that goes up and through sustainment. So it's not a quick answer on how we do get asked every day. The trick is your digital twins will get smarter if you use your new information in the correct way. So thank you.
All right, thank you.
One more comment, Kevin,
Yeah.
just really quick. So I think we get a lot of pressure on this ROI statement again. Well, why should I even invest in validating those models? And I think the reuse of those models, it's not just having a predicted capability that I validate through a test, but back on the sustainment side, where we're doing a lot with prognostic health management, and you think about the Internet of Things, how do I monitor a fleet of assets and understand their reliability and availability back to the physics-based model? There's all kinds of interesting reuse opportunities for these digital twins that you can plug in to lower that sustainment cost on the tail end if you have a model you trust.
Right.
So it starts with trust, but then the ROI is pretty easy story with massive reuse if you have a model you trust.
All right, audience, other questions? All right, I'll ask a question on behalf of the audience because I heard this morning. So I think it's a fair statement to say that everybody working in A&D, and particularly on the operations sides, cares about the trust and the veracity of these models. And we set the stage this morning by saying, look, we're in a new time now. We've got to move really fast. And I heard several times saying, boy, that validation process takes forever. And in the absence of having a validated model, I'm going to have to make a decision without one. So how do we build that acceleration of the validation of the models into the process now? Are we doing that currently? Is it front of mind when we're in the engineering process thinking, okay, this model that has to come out needs to be validated and used in an operational context?
I think there's some examples of goodness there where we are, and I think we should be careful on verification, validation, right?
Yeah.
I think we're good at verifying that our models are behaving to what we thought they would do, but whether they're fit for intended use on the validation side, I think that is an incredibly complicated question.
Yeah.
And I think I think we likely verified all the elevators on the Ford, but when it came to validation, and those are the coolest elevators, by the way, right? They're like mag lifts, like a magnetic, and they can lift like 4 times the amount of weapon payload, but it was a tolerance stack-up problem, so that's an interesting modeling dilemma. But I'm sure we verified that we were meeting all those requirements, but then the validation of the holistic system, it kind of, that's where we fell apart, right? So I think the validation is complicated, right? It's hard to validate.
Right.
I think there's a certain amount of the validation or verification that's starting to come about when we talk about digital systems and the ability to run at faster than life simulations, right? It used to be with the cars, right? You're going to run thousands of miles and you'd have to use the tracks and you're running over that. But with the digital systems, we're able to connect and run hardware, even hardware in the loop, but digital systems themselves faster than the human operator can run, right? Rather than 159 clicks, it's a system that runs over and over and over and over and over again and collects that data, right? But we can speed more of that up as we distribute the processing power itself. We talked a little bit about cloud computing or cloud capabilities out there. Now there's security risks, especially when you're looking at DoD capabilities, and I think Amazon's trying to take on some of that right now. But the ability for you to distribute the data collection, so it's not just one system, it's not just one ship that's doing the 1 terabit of data, right? But you have a fleet of ships that are all doing this data, collecting this data. Now you have real, live, day-to-day data that's being populated, and there's no way a human can necessarily crunch all those numbers, right? But now you have different sample spots across the country, across the world, and you're able to pull all that data back in that cloud-based operation, the IoT, and then re-sample those models, going back down the other direction and saying, is this being verified in the real world, right? Yeah.
I agree with that statement, and one of the other things that I don't think we do a very good job, right, is at some point you have to validate that the data you're actually collecting is the data that you really need, right? So we may put out a first generation product that has a certain set of sensors, but we may decide that the second generation or third generation or fourth generation has an entirely different set of sensors based upon the performance of the product that we see. And that feedback loop, I'm not sure that we do a very good job at that today. We have a tendency to just put out a product and it stays censored for the entire lifespan of that product, despite the fact that there's probably either more data or additional data or data that we're collecting that we really don't need. And I think that that's one thing that we have to do with regard to the validation of these systems in the future, which is to continually validate that the data that we're getting not only helps us solve the problem or look at the performance of that system, but what either data don't we need or what additional data do we need that we're not currently getting.
Right. Thank you.
Yeah, I was just going to tag onto all that is going back to what I said earlier, where if you're building tools and developing tools simply to meet requirements and to prove a single design and not being deliberate and making sure that can be generic and used across multiple different programs, I see so often that a tool will get used, it'll get put on the shelf, and 3 years later, another program comes along and says, hey, there's that tool we developed, and maybe we can use that because it's already been validated. If you take that and say, oh, shoot, it was based on these assumptions, based on trying to meet this requirement, by the time you're done with it for this new program, you've had to change it so much that you have to go and revalidate it all over again. So if you're very deliberate in developing your tools to be used from program to program and keeping those alive, the validation from program to program goes down.
Great. Thank you, Zach. And with that, I think we've kind of concluded our time here, and I don't want to make anybody late for lunch. So please help me in recognizing the panel for an awesome job and great discussion.